Welcome back. This is video 2. If you missed video 1, it should be on a link before, so go back. If not, this is video 2 with Joseph Monte. We're going to try to make this as quick as possible. So we're talking about hydropower energy efficiency. And all hydropower is a change in potential energy to kinetic. So if you take your potential energy, you store water at a higher point. Where's that pen? Come back here. At a higher point, let gravity do the work and turn some turbine here, potential energy, mass times gravity times height, versus flow rate, kinetic energy is 1/2 mass velocity squares, and you turn a turbine, you can create electricity. Okay, potential energy, we just talked about that. Potential energy, once again, where CP is the efficiency. We normally, at the best case scenario, are looking at around 50%. Okay, now I say around, things change. Piping, you have K factors, which is your friction factor in the pipes or cement channels or whatever. That can be 75. The ideal surface, a frictionless surface, does not exist. It depends what type of flow rate you're looking at. The faster the velocity is, normally the lower this number is. Okay, so if you have something moving 1,000 miles per hour, this friction factor will change dramatically than if it's versus if it's moving at 0.0001 miles per hour, because the friction will be severely different, because then you're looking at turbulent versus flow and things like that. The turbine efficiency, you really can't change that. 80% is about the threshold we get. The gears, 90% is pretty good. You can super cool gears and turbines and the generator to get them up higher, but that you lose energy by super cooling, things like that. So it varies very drastically, these numbers, depending on the size of the plant. The larger the plant, normally the higher the efficiency. That tends to how it works out. Okay, let's move on. Pump storage hydro overview. So I was saying that pump storage is like, we need to look at hydroelectricity like a battery. Okay, what does a battery do? It gives us energy on demand. It's like our phone. We only use it when we want to use it. It's passive. It can be there, but we need to use it when it's there. So pump storage hydro overview is 2 reservoirs, a high one and a low one. Okay, an upper and a lower. And the difference in the left elevation is the potential energy. Okay, so water can be released from the upper to the lower to create energy when you need it. So think of high demand energy things, like when it's really hot in the summer and everyone's running their AC, the middle of the day, a little bit after 5 p.m. when everyone gets home from work and they're turning on all their electronics, or it can change with load. So let's say, like, for some reason you have a plant go down, for whatever reason, in your system, in your electrical system, you can turn this on. And what they do normally at night is they reverse the turbines and pump water from the lower to the upper, thus creating a bigger battery. So 70 to 85% of the energy used to return the water through the pumping system can be regained. So if you want to run your plant at maximum efficiency at night when there's not a whole lot of power consumption, you can do that and pump water upstream, right, to help with your energy generation during the day. The largest capacity, it helps increase the demand fluctuations that are commonly associated with green engineering. It's very hard for solar panels to predict when you need the energy, because the sun does not shine 24/7. The wind does not blow 24/7. But if you pump water up to a pond, you can get it when you need it. Okay, next, pump storage. Okay, the first diagram is a turbine mode, which illustrates the process of generating electricity through releasing water from the upper reservoir. In this case, the valve to the storage pump is closed so that the water freely flows into and spins the turbine, leading to energy being released from the generator to the electrical grid. Okay, the pump mode, which is the second one, is the opposite. The valve of the turbine is sealed and water is pumped from the lower to the upper reservoir with the addition of excess energy from your, let's say, nighttime energy generation to help with the power consumption. Cool. Does that make sense? I explained that last slide. Okay. AEP hydroelectric power. This is in the Appalachian area. We have 17 hydroelectric plants, or 16, and then 1 pump storage. If anyone has ever been to Smith Mountain Lake, it is a pump storage plant. Bet you didn't know that. Cool. Let's move on. Let's talk more about this Smith Mountain Lake project. It was produced in 1965. Smith Mountain Lake actually consumes energy, but the amount of energy generated by the dam is less than the amount of energy that is pumped back to. So it costs more energy to put water into the reservoir than pump back, but they actually use it during peak time. So like I was saying, so it gives them energy on demand, which is what they want, what Appalachian Power wants. Energy on demand. That's the name of the game. So pump storage in Smith Mountain Lake. The normal full pond elevations of Smith Mountain Lake is around 800 feet, but the normal operating range under full pond conditions is considered plus or minus 2 feet. Because of this 2-foot power pool, the normal operating range of the bottom one, which is Lee Lake, is between 600 and 613 feet. Under low flow conditions, Smith Mountain Lake can be at 173, so plus or minus 2 feet. Bath Country, Virginia Pump Storage System, is the same thing. There's a YouTube video associated with it. If you want to Google Bath Country VA Pump Storage System, you can watch that on your own time. But it's nicknamed the Mountain of Power. Mountain of Power. So when its operation in 1850, remember what I said 30 years ago, it's privately owned operating plant in the U.S. Not a huge generator in terms of electrical energy comparative to like Hoover Dam, but it still does a decent amount. How much time do I got? I got 3 minutes left. So Bath Country pump storage statistics. Each of the 6 generating units have an underground maintenance in the last 6 years. So a $60 million project to upgrade to improve the output from 400 megawatts to 462 megawatts. 60 million. The largest pieces are overhead covers, which weigh over 220 tons and therefore have a very high transportation and construction costs. Approximately cost to construct $1.6 billion. It's not cheap. You're not going to get that money easily. This was, what did I say, 85. So we don't really have a lot of these that we're building all the time. They're rather expensive. So let's continue on. Environmental impacts of hydroelectric power. Ecosystem damage, I was talking about this earlier, especially if you have migrating fish. Lowlands, land loss. You actually have more erosion in places that you don't want, or flooding from clogging up this dam right here. This whole area in the back is now going to become a pond. So flow shortage, sedimentation, things like that. You actually get that. How much time do we have? 1:30 from the dam. Methane emissions from reservoirs. So this sounds like sketchy, like, oh no, you don't produce methane from a dam, Joseph, you're wrong. But no, actually things die up here, and they'll decompose in the bottom, and then the gas will be released up into the air. And then the need to relocate people, communities, especially if you have this big water lake around this, and then failure risk. What are the potential damages if this dam fails? So advantages and disadvantages of hydroelectric power. The advantages is once it's built, the power is nearly free. There's really no waste or pollution from the dam. It's relatively reliable. I mean, you're not going to have a dam or a drought that severely cripples your hydropower production. Can adjust for peak power needs. You just adjust the flow rates. Can ramp up or down rather quickly. It's just a valve. Constant generation. You can do constant generation if needed. The disadvantages. They are expensive to build. They are very expensive. And then it's site specific. Every site has to be perfect for the conditions. You can't have faults, fracks, jointings. You relocate the ecosystem, communities, and people, and then the water quality and quantity can be severely impacted. So I'm out of video 2. We're going to have to push this into video 3.